Engineers do this all the time. They worry about the curvature of the road. How come? Civil engineers, guys that build roads and stuff. Why do they worry about that? Because they want cars to stay on the road, right? I mean, that's kind of their job, is to build them so they're safe. So when you drive around a curve, we're talking centripetal force. So the net force on a car traveling around a curve is the centripetal force. And again, nothing new here. Fc equals mv squared over r. Directed toward the center of the curve. For a level curve, the centripetal force will be supplied by the friction force between the tires and the roadway. So it's as you go around the curve, inertia is trying, your car is trying to do what? Keep going straight, but it's actually friction that holds you in that curve, right? And if there is no friction, like if there's ice as you go around the curve, even if you got your tires, your steering wheel turned properly, you're going to do what? Slide right on through, right? We all know that from driving in the rain. Peyton, are you watching? It looks like you're texting. A bank curve can supply the centripetal force by the normal force and the weight without relying on friction. When Jake's dad watches NASCAR, he notes that the banks are curved. They have to be because they're going crazy super fast, right? And friction wouldn't work. Even if you've got really good tires and everything, if the curve is flat, you still got to have some bank to it if you're going past a certain speed. So that's why they bank them. And in fact, you'll also notice that some highway curves are banked as well. Okay? Even if you think about, like, when you're driving into Winnipeg there and there's that cloverleaf as the perimeter meets the Portage Avenue, right? As you're going around that big sort of, curve around, if you look, it's actually banked like this. How come? For safety, right? It's so that there's a little bit of gravity holding you on the road, really. Okay, so let's just get right into it here. So on a level curve. For a level curve, the centripetal force will be supplied by the friction. These diagrams are always hard to draw. So this is the top bird's eye view, and this is the sort of from behind the car kind of bird's eye view, right? So we've got centripetal force acting towards the center, and here we've got the weight force, mg, acting down, and the normal force acting up, right? So quick example here. What must be the coefficient of friction between the tires and the level roadway? Is this what's next one? First on your sheet? This seems... What must be the coefficient of friction between the tires and the level roadway to allow the car to make a curve of radius 350 meters at a speed of 80 kilometers an hour? So we're looking for a coefficient of friction. We're looking for mu. For a level curve, the force of friction is the only force acting on a car and provides a centripetal force. This can be seen from the free body diagram. There's no string, there's no gravity, nothing like that holding you in place. It's simply friction. Okay, so do you have 80 divided by 3.6? You probably don't at the top there, right? They took that 80 kilometers an hour and they divided by 3.6 and you get a velocity of 22.2. Okay? F net, the net force is the centripetal force, which is mv squared over r. Our radius is 350, right? The net force must be horizontal, pointing towards the center of the circle, and only the friction force is available to provide it. The normal force and the weight simply cancel each other out. Calculations are easier if the speed is expressed in meters per second, so there's the conversion there. I apologize. I mentioned that before. Now we can calculate the necessary centripetal force. Fc equals mv squared over r. Notice that we do not know the mass of the car. Is this going to be a problem? Well, let's just sort of leave it in there for the time being. And as you progress through physics, you've probably seen a little bit of this. You're going to see more of it, right? So I've got m times 22.2 squared over 350. The centripetal force is 1.41 m, or 1.41 times the mass of the car, whatever it is. The normal force on the car is mass times gravity, or 9.8 m. Again, we do not know the mass. Don't freak out. We can handle this. We can. For this flat curve, the centripetal force is supplied by friction. Friction is mu times Fn, right? Because mu is equal to Ff over Fn. Looks like part of this got erased at some point. Mu is equal to, or Ff is equal to mu Fn. So the friction force is mu times 9.8 times m. And that's equal to my centripetal force, which was already calculated at 1.41 m. And what happens to the m's? They cancel out. The mass of the car doesn't matter. And your mu is 1.41 over 9.8, or 0.141. Now this means that any coefficient of friction greater than 0.141, because if the coefficient is greater than 0.141, then that means that it's rougher, there's more friction. Will it easily make the curve? Yes. It's when it's less than that it's slippery, it's very smooth, and it slides off here. This is the minimum value for mu. Notice that the force of friction is perpendicular to the velocity, but it is still in the direction necessary to oppose the motion that would occur without friction. The car will slide away from center to the right in this diagram if it encounters a patch of low friction surface, like say ice or oil. Therefore, the friction force is directed toward the center. Notice too that we are dealing with static friction. The piece of the tire in contact with the road is momentarily at rest with respect to the road. We're not talking about the rolling tire. We're talking about that piece of rubber that actually meets the road, as the saying goes, right? It's actually not rotating in that direction, that plane. It's sort of trying to slide. It's at rest. The force of static friction is somewhat greater than the force provided by kinetic friction if the tires start to skid. Once you start to skid, you're in trouble. Okay, so Jake, that basically handles kind of unbanked curves like we talked about yesterday. And I gave you the quick inversion of that yesterday, right, or the day before.
Yeah.
Okay, so let's talk about bank curves now. Civil engineers generally bank curves on roads in such a manner that a car going around the curve at the recommended speed does not have to rely on friction between its tires and the road surface in order to round that curve. We've all seen, maybe you haven't, I don't know, we've all seen curves where there's like a 80 kilometer an hour or 90 speed suggestion, right? Why do they do that? Because there's a curve there that maybe if friction is a little bit lower, maybe you don't have the best tires, you might just slide off the road. Okay, and they're obviously giving you, there's quite a buffer there, cushion kind of thing. So suppose that the radius of curvature of a given curve is 60 meters and the recommended speed is only 40 kilometers an hour, which is pretty darn slow. At what angle should the curve be banked? Okay, and that 40 is really irrelevant. Okay, so you've all seen this picture before, right? About 2 units ago when we talked about ramps, right? So here's the car. Remember this angle here? You've actually seen it more like this, right? But all they've done is just redrawn it up there. Are those triangles the same? They are. And in fact, do you guys know about similar triangles? What does that mean, Brandon? You know, similar triangles? Just means that it's just like a blown up version, right? The angles are all the same. So it's similar to that one right there too, right? Angles are all the same, right? So this angle there is equal to that angle in there, which is equal to that angle up there. Okay, so this is sort of behind the car, looking as it goes kind of around like that. Does that kind of make sense? They're really hard to draw, right? You're looking from behind the car. Oh, that's not good. I got to convert this to. I started this morning and then I got interrupted. Anyways, okay. So what I've done is I've redrawn that diagram there. Oh. I redrew it over here. So it's not going to let me do it now, is it? Anyways, okay. So this triangle right here is what I've redrawn a little bit bigger here. Okay? This weight force is straight down. That would be equal to this side here, F cos theta. This is the normal force right here, F normal. And this is F sine theta, this being sine right there. So consider a car, a mass m going around a curve. The car's weight mg acts vertically downward. The road surface exerts an upward normal reaction force F on the car, or normal force. The vertical component of the reaction must balance the downward weight of the car. So F cos theta is equal to mg. This is equal to this. Not. Got it, Dallas? Am I speaking English? Am I good? Yeah? So mg, Fw here is equal to F cos theta. Okay. The horizontal component of the reaction, F sine theta, acts towards the center of curvature of the road. This component provides the centripetal force mv squared over r towards the center of the curvature, which the car experiences around the curve. In other words, F sine theta, this one here, is equal to mv squared over r. Does that make sense? I'll go back again. This one here is equal to mv squared over r. Why? Because that's this force right here that's doing what? Directing the car towards the center of the circle. The weight force here, mg, is equivalent to F cos theta right there. Okay. All right, here's where the part we got to fill in, and I got to check my notes to make sure I've got this right. In that diagram, this one here, theta, opposite, adjacent, right? And we all know from way back when, tan theta is equal to opposite over adjacent. I'm deriving a formula here, by the way. What is the opposite value? What's the value of this side here? F sine theta. What's the adjacent value? F cos theta. Some of you might be familiar from pre-calculus. Remember doing all that geometry, what do they call that? Trigonometric proofs? Identities. Remember that? That was a lot of fun, wasn't it? Yes, I know. They're terrible. Tan theta is equal to sine theta over cos theta, though, right? Remember that one? That's kind of like the basic one, isn't it? That's about the only one I remember. Tan theta is equal to sine theta over cos theta, right? Okay. But F sine theta, we've already said, is equal to what? Mv squared over r, and F cos theta was equal to, and all this is equal to tan theta, right? Oh, this looks like quite a mess, Mr. Bennett. Any canceling going on here? M's. Tan theta then is equal to v squared over r times g, I think, isn't it? I can show that. If that work doesn't make sense to you, I can show it to you a different way. I just realized that maybe the other way is actually a little bit better. You want me to show it a different way? Yes? I'll leave myself some space here. Okay, so let's go back to this step right here. And let's write that as F cos theta tan theta is equal to F sine theta. I took this, and I just took that F cos theta up there, okay, right? F cos theta was our mv squared over r. Nope, got it backwards, didn't I? Oh. Good old Control Z doesn't work. I'm not earning my money today, you guys. I don't know why I don't have this in Smart Notebook. It makes it a lot harder to write in Word. I guess I just never got around to making it. Okay. F cos theta tan theta F. Okay, this is where I was before. F cos theta is our mg, right? mg tan theta. F sine theta was our mv squared over r. Cancel the m's. Take the g to the other side. Tan theta is equal to v squared over RG. That's the formula that you want. On a banked curve, the tangent of the angle is equal to v squared over r times g. G is 9.8, r is the radius, v is the speed in meters per second, and theta is simply your bank angle. Note that if the car attempts to round the curve at the wrong speed, mv squared over r is not equal to mg tan theta, and the difference has to be made up by a sideways friction force exerted by the car's tires and the road surface. This is the minimum speed you can go around. If it was completely frictionless, okay, we're talking like curling slider on ice kind of thing, right? You could make that curve as long as you banked it at the right angle. Basically, gravity holds you on the curve, right? If you try to go too fast, though, then what? Gravity can't keep up, and there has to be some sort of friction. Fortunately, when we drive our cars, there's always friction. Shouldn't say always, most likely friction, right? Slow down in the winter time when there's less friction, right? Okay. Oh, sure, now it comes back. Nice. Stupid word. Okay. You really want to show me some examples, Mr. Bennett, right? Yeah. Cut out the theory, show me some examples. Okay. Okay, I'm back. Hopefully I haven't lost you completely here. Let's look at this example here. I don't have it written out, so. What is the maximum speed that a 1,500 kilogram car can round a level curve if the radius of the curve is 100 meters and the frictional coefficient is 0.65? Okay, so this is the kind of stuff that a civil engineer would do, obviously much simplified. They've got their highway, it's curved at 100 meters, radius of the curve. They look up what rubber on a road is, and frictional coefficient is 0.65, and they want to know what should be the posted limit that we should post, right? Because it's a level curve, and this is important, because it's a level curve, that means that the friction force is equal to the centripetal force. Friction is providing all of the centripetal force, right? And friction force is equal to mu mg. So in our case here, we've got 0.65, the mass 1,500 times 9.8. I have 9555. 9555 newtons of friction force, which must provide the centripetal force in this case. Make myself a little more room here. Okay? So that must be equal to centripetal force mv squared over r. 9555 is equal to my 1,500. Solve for v squared over 100. Times 9555 divided by 1,500 is equal to v squared. Make sure you take the square root, and you get 25.2 meters per second, which really doesn't sort of mean a whole lot. The civil engineer is obviously going to multiply by 3.6 to give you 90.9 kilometers an hour. I'll let you get that down, and I'm going to ask a few questions. No, but I just wanted to point that out. Just to remind you that you should probably do that. Generally, those kind of questions, when they're talking about roads and stuff, they're wanting kilometers an hour, right? Well, you can't. When you post a sign, they're not going to put a speed limit of meters per second. They're just not going to do that, right? Here's question number one. If they calculated this out to be 90.9 kilometers an hour, what would they put on the sign? Would they put 90, do you think? Yeah, they'd probably put 80, 75. They want to leave a lot of cushion, because if it says 80, how many people are going to drive 80 or less in the room? That's what I thought. Right? So yeah, it's a suggestion. Yeah, they're gonna, and that's based on that coefficient of friction of 0.65. What if there's somebody that hasn't changed their tires in 27 years? Right? Or whatever. So yeah, they're gonna limit that considerably more. Considerably more. The second question that I had was, what was it now? I had two in my mind. Maybe it was, would you put it in kilometers an hour? That must have been it. I don't know. Oh no, I know what it was. Does it matter what the mass of the car is? Did I need to tell you that? What did we do here? This 9555 has 1500 multiplied in, right? So I multiplied by 1500, and then what was the first step over here? Then I divided by it. Does it need to be there? No. In fact, if you go back to what I showed you, right, those masses cancel out, right? In fact, you could just go UMG is equal to MV squared over R, cancel, cancel. Right? Which is a good thing, because do you want curves to be safe regardless of what the size of the car is? Absolutely, right? So yeah. Okay. I'll do example number 9, then I'll be quiet. You had enough listening to me, I'm sure. A race car travels along a bank curve at a speed of 120 kilometers an hour. That's more like it. It doesn't depend on the force of friction to keep it on the track. If the turn is baked at an angle to a golden crisp, at an angle of 25 degrees to the horizontal, what is the radius of rotation? What is the radius of the curve have to be? Now, if you've got a really sort of wide curve like that, or a tight curve like that, which one do you have to go slower on? The tight curve, right? If you see the F1 cars that going around, like, you know, downtown Montreal, and they go over and make those hairpin turns, they got to slow right down and then speed right up real quick. Kind of thing. NASCAR, they want to just go fast all the time. Okay, so I think I said the formula was tan theta was equal to what? And here's the one time I didn't actually write it down on my sheet here. Now this is the one I can never remember. V squared over RG. Not one I use in a lot. And what do we know? I want to know the radius of rotation. So the angle is baked at 25 degrees. 120 kilometers an hour. Can I just plug that in for V? I should convert, right? 120 divided by 3.6. Do I have that number? I don't. How much is it? Oh, here's one. Does it say on the sheet? Oh, it does. 33.3 in the diagram that I stole somewhere. So 33.3 squared over radius is what we're solving for times 9.8. Do some algebra magic. R is going to be equal to what? Can you manipulate that in your head? 33.3 squared over what? 9.8 times tan 25. Make sure you put brackets around that in your calculator, because you're dividing by that whole thing in the bottom. 33.3 squared divided by bracket 9.8 times 2510. I get 242.6.7. 242.7 meters. That would be your curvature. I met up with a friend of mine that's a civil engineer one time, and I think I actually told you guys this, but we were talking about this a little bit because I was just doing it in class. He says, oh yeah, he says, I'll send you a document. He sent me this thing that was like about 100 pages thick that was sort of like their manual, their Bible on how to do all this stuff. So obviously we've simplified it considerably. There's stats involved about, you know, the statistical error of the coefficient of friction. Depends a lot on how good the tires are, weather conditions. There's lots of things they have to take into effect, I think. But they have to survey that out. They got to figure out what's the curvature of that highway to make it sort of so that it's safe, but it's not using up too much space out of town, right? Because they want to make the curve much wider, like I showed. But then, of course, then you get into the money, right? They got to compensate farmers for landowners if they're building a new highway. Kind of thing. So, okay, so you've got. Did you guys get the questions on the back there on yours? I think there are, right? Okay, so you've got, and because they can be a little bit tricky, I've broke them into two parts here. So there's 6 that are unbanked, and there's a few that are banked. There's a really crazy, 7 and 8 are really crazy hard. I don't think I've ever had anyone actually show me an actual solution for them. I got an answer from somewhere, but I don't think that, I haven't been able to come up with a good solution for 7 and 8. So those are extra bonus challenge. Okay. If you can do them, you are set. So be aware, you got to be able to do an unbanked curve and know the theory behind that, and you got to be able to do a banked curve and sort of know that theory behind that as well. So I'll be quiet now. Enjoy.